So now we have y equals e to the x over natural log of x. Who knows what this graph looks like? You can't draw a picture. If you can draw a picture, you can assess it pretty fast, but we don't know what this picture looks like, right? So, crazy function. All right, let's find the horizontal asymptotes. Let's do the limit as x approaches infinity, and then we'll do the limit as x approaches negative infinity, and see if either one of those gives us an asymptote. Now, what are the rules of infinite limits that we've talked about so far? Just take it and plug it in. And if it doesn't work, well, we have to have other approaches that we learned today, don't we? Okay, so step one, take infinity, plug it in, e to the infinity over natural log of infinity. Okay? All right, now remember, you can't ever get to infinity. So let's approach it. E to the gigantic, heading to infinity. E to the gigantic is infinity. What about natural log of infinity, though? Well, if there's a horizontal asymptote, it would be that number. But if there's no boundary, then when you go to infinity, you go up to infinity, right? The natural log graph, it climbs, it levels, but it never truly levels, does it? It's always going higher and higher and higher. Remember our whole discussion in 10-2? When you go to infinity, the natural log of x also goes to infinity because there's no boundary. There's no horizontal asymptote or cap on top of it. Uh-oh. Okay, for the first time today, we got infinity over infinity. The whole day we got away with plugging in infinity every time until now. Infinity over infinity is indeterminate form number 2. It tells you nothing. That's a dead end. All right. Do we have a backup plan? Yes, and we kind of discovered it in the last problem we did, letter E. In letter E, do you notice that when we went to infinity, we ended up getting 0? That was interesting. Only certain kinds of graphs are asymptotic to the x-axis, y equals 0. So let's dig into that just a little bit because there's a little game you can play. And I call it the weaker, stronger game. All right? So weaker, stronger game. Okay, let's think about this. Wasn't the function in letter E, wasn't it 1 over x squared plus 1? Okay, who's weaker, numerator or denominator? Well, the denominator is an x squared at the highest power. The highest power of the numerator, isn't that technically x to the 0, right? Okay, 1 is just x to the 0, right? So the weaker one is the 0 power. The stronger one is the second degree polynomial on the bottom. The weaker one will always collapse to 0. Now that could be really helpful. So you find the weaker between the numerator and denominator. And when you go to this, by the way, this only works to positive infinity, not negative infinity. But you can use this for positive infinity. The weaker one becomes essentially worthless compared to the strength of the other one. So just leave x squared plus 1. And then 0 over x squared plus 1 is 0, and that's the exact answer we got when we went to positive infinity on the front page. It comes in handy here because on the front page we had other methods that worked. Here, you don't have any other outlets. You have to basically know the weaker, stronger game, all right? So let's take a look at the numerator and denominator here. And we're looking at e to the x versus natural log of x. Well, guess what? E to the x is way stronger than natural log of x, right? That's a slowly rising function. That's a quickly rising function. I mean, the only way to beat e, which is about 2.7 to the x, would be like 3 to the x would be stronger. 4 to the x would be stronger. 5 to the x. So stronger, weaker. Okay, what did we say? In the weaker, stronger game, you can let the weaker one turn into 0. So that would be e to the x over 0, right? When you have a 0 on the bottom in math, it is undefined, does not exist. In other words, the limit as x approaches infinity does not exist. So there is no horizontal asymptote when you go to infinity. Now there could be one going to negative infinity, but there's not one going to positive infinity. Okay? So, weaker one on top, make it a 0. 0 over anything is 0. Weaker on the bottom, make that a 0. Undefined, no answer. Boy, is that a time saver now that you know that trick, right? And this was, pretty much the only way you could do this one. Now, don't forget to check going to negative infinity, okay? E to the x over natural log of x. Again, we'll try method number 1 first. Plug it in, see if you can get away with it. We've gotten away with it today. If you can't, we'll try new games. Unfortunately, the weaker, stronger game only works for positive infinity. So we're going to be in trouble if it does not work here for negative infinity when we plug it in, because you can't go to the weaker, stronger game. We'll talk more about that too. Let's see if it works. Usually it does. All right, so you get e to the negative infinity over natural log of infinity. As per the front page, don't you always move your e to the negative down to the other place? But here's the problem right here. You can't take the natural log of 0. You can't take the natural log of a negative number. You can only take the natural log of a positive number, correct? There is no natural log of a negative number. That's impossible. One little impossible ruins the whole thing. The whole thing becomes d and e. So actually, it wasn't even really, I mean, we plugged it in, but it wasn't really a limit after all. It was just kind of knowing your earlier natural log things from, topics from integrated 3, really. All right, so there are no asymptotes in this case. So good, though, that we saw the weaker, stronger game because it's so important. So in letter G, we've got this example here. It's some function. It's way too complicated to graph, right? Because remember, if you can draw a graph, just draw a picture. So you look at this thing and you're like, okay, where are the horizontal asymptotes? All right, well, let's go to infinity. Let's go to negative infinity. Okay, limit as x goes to infinity, first of all. Okay, let's just save time. Let's draw an arrow. All right. When you go to infinity and you take the limit of this function, if you plug infinity in, which is always our first tactic, right? This is our first attempt. If you plug infinity in, you get infinity plus infinity, which is infinity, over infinity plus 1, which is infinity. Oops. Indeterminate conversations. Remember the fireplace? Okay. That doesn't tell you anything at all. All right. Level 2. Bring in the weaker, stronger game, right? But now, wait a minute. I've got to tell you this. The weaker, stronger game only works under certain conditions. Why did it work for the one on the front page, letter E, and why will it work for this one? Do you see how the numerator 2x cubed plus x is a polynomial? All right. You remember polynomials, right? Just your typical x to the power. There are no square roots. There's no over x. They're just normal, ordinary algebraic functions, right? The top is a polynomial. The bottom is just a standard third-degree polynomial, 3x cubed plus 1. The weaker, stronger game works when you have a polynomial over a polynomial, like letter E, like letter G. It works under one other condition. Did you see the last example? E to the x was not a polynomial. That's exponential growth. Natural log of x wasn't a polynomial. That's logarithmic growth. If it's a single term over a single term with nothing else added or subtracted from it, just two single terms, you can always use the weaker, stronger game for your positive infinity limits. All right? So single over single. So these are the two times that I'm actually applying, and those questions are common. So when you see that, you just apply the weaker, stronger game. Okay, so you plug in infinity, dead end, indeterminate, weaker, stronger, polynomial, polynomial, it's on. All right, find the weaker one, make it dissolve into 0. Remember the game? Who's the weak one? You become 0. All right, who's weaker? Uh-oh, we got a new thing here. In letter E, the top was weaker. In letter F, the bottom was weaker. In letter G, they're tied. X to the third and x to the third are the highest powers of x on the top and the bottom, and that's a tie. So that means we're at even strength. Uh-oh. What do we do when we're at even strength? You can't pick a weaker one. Okay, let's put this. Same over same. Okay, same degree. Two third-degree polynomials. When they are the same, your limit is not 0. Does not exist. Your limit is the coefficient of the highest power divided by the coefficient of the other highest power on the bottom. 2 over 3, 2/3. If you plug in like 1 million on a calculator for all three of these x's, you'll get a number that's about 2/3. If you plug in 1 billion, you'll get a number on the calculator that's about 2/3. It's trying to get to 2/3. It's a horizontal asymptote. That's the answer. All right? Matter of fact, I'm curious as a cat. Probably what my friends call me Whiskers. I actually tried, what did I try? I tried 100. I didn't even go that far. All right? I just tried 100. And you know what happened? When I plugged in y of 100 into this equation, you can easily do it on a calculator. It was approximately 0. What did I get? 1, 2, 3, 4, 5. No, I got 4 sixes. Sorry. 4 sixes. 6, 6, 6, 6. I'm not going to say 3 sixes. 9, 9, 7 repeating, and then the 7 just repeated. Okay? Did you know that 2/3 is 0.666666666 forever? Right? 2/3 is 0.6 repeating. That's only a tiny bit above 0.6 repeating. And I only went to 100, and it's practically become 2/3 already. Okay? I actually plugged in also 1 trillion. And I got 1, 2, 3, 4, 5, 6 sixes. But there wasn't much difference when I plugged in a trillion. It was pretty much the same thing. That's the thing. You're already at the asymptote when you get to 100. Okay, let's do one more thing. So we got y equals 2/3 as one answer. What about the other limit? Now, this is not going to be the weaker, stronger game because you can't use that for negative infinity. What about the other limit as you approach negative infinity? Okay, let's take this, put this down here. If you plug in negative infinity cubed is negative infinity. Negative infinity in for x is another negative infinity. Negative infinity cubed is still negative infinity plus 1. Okay, first, plug it in. What do we have here? Lose everything and then lose everything. Isn't that just negative infinity on top? Let's put that down there. And then negative infinity, but I got back $1. Well, you're still at negative infinity. Okay, negatives cancel, but that's not even the point. It really is infinity over infinity in spirit. That is indeterminate. It does not help. Weaker, stronger game does not work for negative infinity, only positive infinity. So the two things we've relied on so far don't even work. There is only one option remaining in today's lesson. And it's a nice little trick. Let me rewrite the function down here. Okay, when you're going to negative infinity, when the plug-in fails and you can't go to the weaker, stronger game, there is one thing that works almost every time. Pick the highest power of the denominator, not the numerator, believe it or not, only the denominator. Then put 1 over x to the highest power that appears in your entire denominator. So 1 over x cubed, you don't need the 3 at all, okay? We're going to distribute that through the bottom. But if you do it on the bottom, you have to do it on the top. Okay? So all that matters is the highest power of the denominator and that you make it into a reciprocal and distribute it. Now watch how cool this is. This is like your worst case scenario, but it's going to happen, of course, on the test somewhere. It's going to happen on the AP test too. 1 over x to the third times 2x to the third. When those multiply, you cross cancel the x cubes and you get 2 times 1 is 2. Okay? When you multiply and distribute to here, you cross cancel 1x from each one, right? That's x over 1 anyway. Cross cancel a single x and you get 1 over x squared. Okay? Now, distribute this one to there. The x cubes cancel as soon as they contact each other and you're left with 3. And then 1 over x cubed times 1 is 1 over x cubed. They'll actually make you do this in college, by the way. You have to actually prove the weaker, stronger game. This is the proof, kind of. But in college, they won't let you just say, by the weaker, stronger game. That's a Mr. Wadeism. You have to prove it this way, so this is good to get used to here. Now that you have this new form, you know it's right when every x that appears is underneath, and pretty much every term is either an x underneath or just a constant all by itself. There are no x's left on the top, either with the 2 or with the 1 or with the 3 or with the 1. That's when you know that you're in the right place. Now you retry the infinite limit. So this is, you'll have to do this maybe once on the test when we get to it. Worst case scenario, last attempt, plug in negative infinity to all the x's. So this whole function goes over here. Okay? And let's plug in negative infinity and see what we get. And I've put it back at the top of the board here and kind of erase some space so we can, do this a little cleaner, right? But worst case scenario, we got to here. Take negative infinity, plug it in for the x, and this should work. 2 unaffected by x plus 1 over negative infinity squared is positive infinity. All right? 3 plus 1 over negative infinity cubed is negative infinity. Make that plus minus into a subtraction, obviously, right? But here's the point. 2 plus 1 out of infinity is 0. So you get 2 plus 0 on top. 3 plus minus makes a subtraction. 1 out of infinity or 1 over infinity makes a 0, right? 2/3. Is it always the same as the other one? No, it's not. That's why you have to work this out, because you never know if it's going to be something different. This time, it happened to be the same outcome. And by the way, we just kind of proved the weaker, stronger game for positive infinity. All right? But the answer is 2/3. So it happened twice, negative infinity and positive infinity, but you would only have to write it once, y equals 2/3 as your official horizontal asymptote. Interesting stuff. And that brings us to 3 gems on your notes. And I believe, now let me think, I think this might be the first time we've had gems in this class the entire year. What is a gem? All right. A gem is something you will not find on the internet. You will not find it published in textbooks. The college professors will not tell you this. Most of your high school teachers will not tell you this. Gems are things that either my father, the world famous mathematician during his lifetime, or Mr. Wade, based on his own research, discovered. So these are our own discoveries that are not published anywhere, that other people know about, they just never say it. When you get to college, they don't tell you the rules, they just throw math problems at you. Well, I'm going to teach you how to handle anything they throw at you in college. So, on that note, for the first time this year, I think, let's go to the gems. And now we have our 3 gems right here. This is what they don't tell you about infinite limits. Now, before the gems, of course, let's go back to 10-2. Remember, if you can graph it and draw a picture, just draw the picture, because then you know all the answers if you know how to graph the function, right? The easy ones. But let's say you don't know how to graph it. Okay, here's how you attack infinite limits right here. So this is all for infinite limits, right? All right, step number 1. Didn't we say just plug in infinity, right? Or negative infinity? Just plug it in. It works most of the time, all right? If that doesn't work, step number 2, only for positive infinity, right? So let's say only for positive infinity. If you let x go to infinity, you can do a little weaker, stronger game. Okay, compare the top and the bottom. It's a comparison. But it only works for, what did we say? If you didn't write this down yet, put it down now. Polynomial over polynomial, or a single term over a single term. And that's the only time that's going to work. All right? So this is your order, because when you do the first one, plug it in, it usually just solves all your problems. Okay? That's why I put it in a specific order. If that doesn't work, automatically go to this one, because that's usually going to solve the rest of them. And then rarely do you go to step 3. Step 3, which will work for positive or negative infinity. We just did it for negative infinity, but it works for either one. Put 1 over x to the highest power of denominator. See if you can write all that like right up there as a little tiny superscript exponent. 1 over x to the highest power of the denominator. Put that on the top and the bottom, and then it should work out. Even the weirdest cases should work out just fine. Okay? And only when you get to like some crazy stuff in Calc 2 would you eventually see cases where none of this would work, and they kind of give you an out. They give you like, and matter of fact, even this year, I'm going to show you like one more out that you could use just in case none of this works, but like 99.9% of the time, you're going to be just fine using this, okay? Gems, not published on the internet, not in any textbooks. You won't find it anywhere. That's just for you, your benefit for being in my class. Take it to college, use that. I use it all the time when I'm explaining these answers, by the way. Okay, now we go to letter H. I'll just kind of do this on the fly. Limit as x approaches negative infinity. So this is a type of infinite limit, isn't it? Already I'm thinking about my 3 gems. 4x squared minus x minus 1 over 5x plus 2. Okay, so step number 1. I take negative infinity. I try to plug it in. Let's see if it works. All right, negative infinity squared is positive infinity. Positive infinity times 4 is positive infinity minus negative infinity. Minus minus becomes a plus infinity. Minus 1. Over negative infinity times 5 is negative infinity plus 2. Let's see if that helped us out here. Infinity plus infinity is infinity. Minus 1 is infinity under the square root. And infinity plus $2 back. I'm still in debt, infinite dollars. So it's still negative infinity. And by the way, yes, the square root of infinity is infinity. Doggone it. You know what we got? This usually works, but we got infinity over infinity with a negative in there, but it's still infinity over infinity. Indeterminate. Case 2. Attempt 2. Use the weaker, stronger game. Well, that doesn't work for negative infinity, only for positive infinity. So we can't use it. Number 3. Gem number 3. Try to put 1 over the highest power of the denominator. Only the denominator, not the numerator. Because there are some weird cases where it doesn't work unless you do the denominator. So always do that. So, isn't x to the first the highest power of the denominator? So I'm going to put 1 over x to the first without the 5 and distribute it and try to rewrite this whole thing. And if I do it to the bottom, I do it to the top. Uh-oh, anybody see a problem? I already see a problem up there. Let's get this out of the way. You can distribute across the bottom, no trouble at all. Let's do that first. Okay, the denominator is not the issue, the numerator is the issue. 1 over x times 5x, the x's cancel and you get 5. Okay? 1 over x times 2 over 1 is going to be 2 over x. What about upstairs? This little dog right here, his name is 1 over x. Come here, 1 over x. Come here, 1 over x. Come here, boy. Right? That's a great name for a dog, 1 over x. All right, 1 over x wants to play with the other dogs. But the other dogs are locked inside a fence called a square root. That's not a parentheses, which is unlocked. That's a parentheses to the 1/2 power, and the 1/2, any kind of power, is a lock. The dog can't get in to play with the other dogs. How sad. Unless maybe we could like sneak him under the fence somehow, right? We could, and I believe we did it in the first semester a long time ago, all right? This was way back. Do you know what you could do? If that 1 over x were under a square root itself and they were both under the same fence, they could play together. Let's put a square root around it. Isn't the square root of 1 still 1? So that's actually the same, but the square root of what gives you x? Isn't the square root of x squared x? Would you agree that the square root of 1 over x squared is actually 1 over x, but in disguise? So you put a square root over it. You square the bottom and you technically squared the top, but 1 squared is 1. You square both the top and the bottom, you put the square root over it. Squaring and square rooting would offset each other. So under the same fence now. 1 over x squared times 4x squared would cross cancel the x squareds, and you would get 4. 1 over x squared times minus x, okay, minus times a plus is a minus. One pair of x's would cross cancel there, but you'd still have 1 over x. And finally, 1 over x squared times negative 1 is negative 1 over x squared. We have rewritten it. Now this is, remember, this is supposed to work. This is the third gem, last attempt, right? Desperation right here. It should work. Did everybody end up with an x on the bottom or no x at all? Yes. No x's on the upstairs. That's perfect. That means you did it right. Now take negative infinity and plug it in and watch the answer leap out before your very eyes. 4 minus 1 over negative infinity minus 1 over negative infinity squared is positive infinity over 5 plus 2 over negative infinity. And now watch the magic unfold, my friends. 4 is 4. Minus minus makes a plus, but that doesn't matter because 1 over infinity is 0. Minus 1 over infinity is also 0. It's 4 plus 0 minus 0 over 5. Plus minus makes a subtraction. but 2 out of infinity is 0. And that's why this clever game of 1 over the x to the highest power of the denominator works, is because it just makes everything dissolve except for the important stuff. All the stuff that didn't matter becomes 0, and the stuff that does matter, it kind of stands out like a sore thumb now. And finally, 4 plus 0 minus 0 is 4 under the square root. But of course, the square root of 4 is going to turn into a 2. And by the way, we used to call this the sneaky dog trick. If you remember the first semester, it was the sneaky dog, and it was like an old, it was like an arc sine derivative, and we had to sneak the dog under the fence. It's that thing again. And then on the bottom, 5 minus 0 is 5. So the final answer is 2/5, and the only way to do that problem in all the calculus you'll ever learn in high school and college is to do that trick with the 1 over x to the first. It's the only way to do it, with a little twist of a sneaky dog in there as well, okay? And you find the answer is 2/5. There is no other good way to do that problem, all right? And there you go. Now, was this a horizontal asymptote? No, it just said find the limit, so leave the number because that's a y coordinate. It really is a horizontal asymptote though, right? Because it's an infinite limit going to the left. If it says asymptote, put y equals 2/5. If it says limit, leave it at 2/5. Okay, now try some of that homework and see if you can get through the hierarchy of what you're supposed to do with infinity in what order, because I worked through all these problems and I figured out the best way for you to do it. So follow Mr. Wade's gems, and I'll see you next time. Hold it now. I didn't make a typo. On the paper, it says % charged, and then on the board, I had accidentally written % changed. Clearly it says charged, so that was not a typo, that was a speako. We'll have other concepts? Hasn't been like a, you just, and technically that is absolute.